So what we're going to do here is look at Kepler's third law after you've done the Kepler's third law lab. In that lab, you should have seen that a cubed is proportional to p squared, where a is the semi-major axis, measured in AUs. That's an astronomical unit. That is the distance between Earth and the Sun on average. In the orbital period, all right, that is the measured in Earth years. So this is another version of it where k, some constant, is equal to a cubed over p squared. Newton came up with this where k is actually, for everything in our solar system, is just 1. So in other words, you could really set a cubed to p equal to p squared. But that k, that value, is actually not the same if you looked at other objects, say, for example, the moon going around the Earth or moons going around Jupiter. So the question is, what is that k, that value, actually representing? And in fact, it's actually the mass of whatever object is being orbited. All right. So if you're going to measure the mass of our sun, we can use or do that calculation by taking the motions of any object that's orbiting it. If we want to measure the mass of the Earth, we can figure out its mass if we look at objects going around it, like satellites or the moon. So k, when we're actually using it, all right, we'll actually be calling it m, the mass of whatever that central object is. It's really the sum of those two. But normally, that central object, for example, our sun, is so much larger than the objects going around it. Say, for example, if we look at the largest planet, Jupiter, compared to the mass of the sun, the mass of sun is 1,000 times greater than the mass of Jupiter. So we can really ignore the mass that the planet would add to that system. And we measure that mass in solar masses, m with a little subscript that kind of looks like a bullseye, a circle with a dot in it. That's a really important unit to remember. That circle with the dot in it is a solar unit, because we'll be measuring luminosities in solar units, or radii. In this case, we're using mass. So always know that that little circle there is representing the solar unit. In this case, solar masses. All right, and our sun is the benchmark that we're going to compare everything else to. All right, it has a mass of 1 solar mass. Stars that are twice as massive would have 2 solar masses. So let's go ahead and do a practice calculation. Let's say that we observe a planet orbiting around a star, and its average distance is 2 astronomical units, and it has a period of 3.5 Earth years. How massive is the star orbiting it? Now, what we know is that semi-major axis, A, is 2 AU. We also know that the period is 3.5 years. Well, if we want to solve for the mass of that central object in solar units, all we have to do is take a cubed over p squared. So we plug in those numbers. 2 cubed over p, 3.5 squared. If you want to actually do the calculations, that works out to be 8 over 9. You don't have to do that part in your work, but if you want to, that's fine, which gives a central mass of that star of 0.88, repeating. All right. So we'll just round that up to 0.89 solar units. And that's all we have to do. We take those two numbers, plug them in, and done, as long as our units are in the proper units. So semi-major axis must be in AUs, and the period must be in years. Let's try using Kepler's third law, though, to weigh the Earth. All right. We do know the motions of the moon. A synodic month, or excuse me, a sidereal month is 27.3 days. That is the 360 degrees orbit around the Earth of the moon. But as those are in days, we need to get those into Earth years. So there's 27.3 days, 365 days per year, which gets us 0.002569 years. We also know that the distance, if we're going to put it in miles, is 235,000 miles on average. And if 1 AU is 93 million miles, all right, we can convert miles by dividing the 235,000 miles by 93 million miles per AU and get a distance of 0.07479 AUs. So now we're in the correct units of years and AUs. We can use the equation to actually come up with that the sun is, or the Earth is 0.000003 solar masses. It's a very, very small amount. So that's basically what we need to be able to do from this VCAS. We need to be able to calculate the mass of the central object. That could be a star, it could be a planet, or some other phenomenon that you'll look at when you do your practice calculations.